Year 13, Chapter 18, Kinematics, Lesson 1, Motion in 2 Dimensions. So we're going to begin by recapping the constant acceleration equations. Some of you may have perhaps referred to these as the SUVAT equations. Let's see if we can write all 5 of these equations down. So let's check that we've got all of these correct. S equals ut plus a half at squared. S equals vt minus a half at squared, v equals u plus at, s equals a half u plus v multiplied by t, and v squared equals u squared plus 2as. Make sure that you understand what each of the symbols represents in this set of equations. So s represents displacement from your starting position, u is initial velocity, v is final velocity, a is the acceleration, which must be constant if we are to use these equations, and t is the time taken. So we're going to have a look at a few examples of the variety that you may have seen in Year 12 kinematics, just to recap using these constant acceleration equations. We have a car travelling on a straight road at 20 metres per second when the driver sees a tractor blocking the road 30 metres ahead. The driver hits the brakes and the resulting deceleration of the car is 5 metres per second. Find the speed at which the car hits the tractor. So I'm going to write down all the information I know. I know that there is a distance of 30 metres between where the car is and where the tractor is. So I'll take s as 30. U is the initial speed or velocity of the tractor, which is 20. V is what we're actually looking for. A, the acceleration, is negative 5 metres per second as the driver is braking, so decelerating. And t, we do not actually know. So we might actually rule that one out as we can't use it. So which SUVAT equation contains the information I need, S, U, V and A? It is the equation v squared equals u squared plus 2as. So we can substitute directly into that. And this then gives us a value for v squared, which is 100, which then gives us v equals 10 metres per second. So here's another example. A ball is thrown vertically upwards with a speed of 29 metres per second. It hits the ground 6 seconds later. Modelling the ball as a particle, find the height above ground from which it was thrown. So it looks like we have this sort of situation. There's the point at which the particle or the ball is thrown upwards, goes up like that, and then it hits the ground like that. So we know it's thrown vertically upwards with a speed of 29 metres per second. We know at the top of the motion here, the speed and the velocity would equal 0 at the maximum point above which it was thrown. And we know that over here it hits the ground 6 seconds later. Now we need to find this distance here, the height above ground, this is the ground, from which the ball was thrown. So here is what we're going to do. We're going to set up a SUVAT equation. But before we do that, we need to mark on a missing piece of information. We know that this is vertical motion under gravity, so the acceleration is downwards and is equal to g, or 9.8 metres per second squared. Now, because the motion involves 2 different directions, we need to be very clear about which direction is positive. I'm going to choose up as the positive direction because initially the ball is thrown vertically upwards. So we're going to fill in as much information as we can, and I'm going to look at the journey from O to, let's say, this point here. So I'm modelling the journey from O across to P. Now S, we don't know what that's equal to. I could call it negative x, because it's x below the origin, the starting point. U is equal to positive 29 metres per second. Remember, it's upwards. v, we don't know what the velocity is. A is equal to negative g, acceleration acts downwards, and t is equal to 6 seconds. So what we can do is rule out this because we don't need to calculate the velocity, and then this leaves us with s equals ut plus a half at squared as the SUVAT equation that links everything. So negative x is equal to 29 multiplied by 6 plus a half multiplied by negative 9.8 multiplied by 6 squared. What does that then give us? Well, it gives us negative x is equal to negative 2.4, so x is equal to 2.4 metres. So the particle was released 2.4 metres, or thrown 2.4 metres above the ground. Now, if we had just said that s was equal to some value, we didn't call it negative x specifically, then let's see what would have happened. Well, we would have then had s equals 29 multiplied by 6 plus a half multiplied by 9.8 multiplied by 6 squared, and we would have got the height above ground to equal negative 2.4 metres. Now the negative just tells us that we are 2.4 metres below the origin or the starting point. So remember, at the very beginning of this question, we identified that up was positive, which means down is negative, and this allows us to interpret positive and negative results accurately. We're now going to consider the motion of a particle in 2 dimensions. So let's set up a pair of axes. We'll call the x-axis the I-axis and the y-axis the j-axis. Now let's imagine a particle moves on a path, or trajectory as we can also call it, from the origin, and it travels along this straight line marked in red until it reaches this point here, which we'll call P, which will have coordinates x and y. Now, we would say that the particle at P has a position vector which we would call r, and r has an I component of x and a j component of y. You may also be familiar with writing this in the format of a vector x, y. Now, we can calculate the distance travelled by working out the magnitude of this vector r, which of course we can calculate using Pythagoras' theorem. Now, because we're looking at motion in 2 dimensions, we have to be specific about a direction of travel. So we might want to calculate theta, this angle here above the horizontal, using trigonometry. Now, if you've learned a little bit about motion or vectors in 3 dimensions, you will know that a position vector for a particle moving in 3D space could be expressed in the following way. We could write the position vector as x, y, and z. So it's got an x component, a y component, and a z component. And if we wanted to write that in vector form, we would write xi plus yj plus zk. And if we wanted to work out the distance travelled, we would then carry out a Pythagoras theorem calculation, but with all 3 components in the following way. But that is purely when we're looking at 3D, or motion in 3 dimensions. So coming back to the concept of motion in 2 dimensions, if we know acceleration is constant, we can convert the SUVAT equations from being equations that work essentially in 1 direction to equations that can work in 2 dimensions, so to vector equations. And here they all are. So, one point to note is that rather than using the letter S, we tend to use the letter R for displacement. So you'll notice that S has been replaced by R in the SUVAT equations. So first of all, we know we have S equals ut plus a half at squared. That becomes R equals ut plus a half at squared. So notice that displacement, velocity and acceleration have all been expressed in the form of vectors. Now let's see what happens to the other equations of constant acceleration. We know we have s equals vt minus a half at squared. That becomes r equals vt minus a half at squared. Again, displacement, velocity and acceleration all being expressed in vector form. Now we also know that we have v equals u plus at. We can convert that to vector v equals vector u plus at. Notice, of course, time is not a vector quantity, it's a scalar quantity, so it's expressed just as t, not as vector t. And we then have s equals u plus v over 2 multiplied by t, and that becomes r equals u plus v over 2 multiplied by t. And again, displacement and velocity are both expressed as vectors. Now, notice there is no vector equivalent of the SUVAT equation v squared equals u squared plus 2as. That is because we do not know at this stage how to square a vector. It just doesn't make sense to us based on the knowledge of vectors that we have. So we rule out the equation v squared equals u squared plus 2as, and we just make do with these four equations. Now, one last point of note here is that all four of these equations here work when the initial displacement of our particle or our object, which is moving in 2 dimensions, is at the origin. So its initial displacement is the 0 vector. Now, if the particle happens to be at a point which is not the origin at its start of motion, we can adapt these equations, or some of these equations, as you have seen previously when dealing with SUVAT equations and constant acceleration problems where the motion doesn't start at the origin. So if the initial displacement of the particle is at a point with position vector r equal to r0, which is not the origin, not the 0 vector, then the equations for displacement, equations 1, 2 and 3, can be converted as follows. So equation 1 becomes r equals ut plus a half at squared plus r0. So we're simply adding on the initial displacement of the object. Equation 2 becomes r equals vt minus a half at squared plus r0. Now, equation 3 can stay the same because that is an equation about velocity, not displacement. But equation 4 becomes r equals a half u plus v multiplied by t plus r0. So in each case, we can calculate the overall displacement from the origin by adding on the initial displacement vector. This is illustrated in a little bit more detail in the next diagram. So let's look at these two scenarios in comparison with each other. Let's suppose a particle starts at the origin. We know the particle is moving with constant acceleration. Let's say it moves to some point over here. So there's the origin, and then there's the new point here. Now, this displacement can then be calculated using any of the 3 constant acceleration equations for displacement that we saw on the previous page. Now, let's see what happens when the motion does not begin at the origin. Let's imagine that the motion begins at this point here, which we will call A, and that the particle travels with a constant acceleration from point A across to point B. Now, let's say that point A has a position vector of r0. Now, if we then use any of the SUVAT equations to calculate r, it will give us the displacement from A to B. Remember that we're timing this whole thing so that time t equals 0 starts when the particle moves from point A. So our SUVAT equation will give us the displacement vector AB, the displacement of B from A relative to A. But if we want to find the overall displacement from the origin, so O to B, then we need to work out OA plus OB. Look at the diagram. The vector OB, which I'm going to draw on in bright green, looks like that. Can you see that green vector is the vector sum of the blue vector OA, which is R0, and the red vector AB, which is our vector R, which is what we get from the SUVAT equation. So this links back to the previous page where we said if you want to get the overall displacement from the origin and you didn't start at the origin, you then need to add on your vector R0 so that you get the complete triangle of vectors here. So remember, when you apply your SUVAT equation, it will only give you the displacement from your starting point. So if we apply a SUVAT equation in this situation, we will get the vector AB, which is fine. But if we want to know the position vector of point B relative to the origin, i.e. the vector OB, then we need to make sure we add on the initial position vector of the object, its starting position vector, which is the vector R0. Let's have a look at two examples of situations where we will use the vector equivalent of these SUVAT equations. So we have a particle which leaves the origin with a velocity of u equals 2I minus 3g meters per second. Notice the vector velocity we're given here. It travels for 5 seconds with a constant acceleration until it reaches a velocity of v equals 6I plus 5j meters per second. Now, part 1, we need to calculate the magnitude of the acceleration of the particle. So let's write down what we know. And we are applying the SUVAT equations again, but we don't have scalar quantities. This time we're dealing with proper vector quantities. Now, I don't know anything about the displacement, so that's an unknown. The initial velocity is 2I minus 3j. The final velocity is 6I plus 5j. The acceleration is what we are actually looking for, and the time is 5 seconds. So let's rule out this quantity here, r, and let's look at the fact that we can use v equals u plus at here. So we can say that 6I plus 5j is equal to 2I minus 3j plus 5, which is the time multiplied by the acceleration. And we know how to add and subtract vector quantities. So if I subtract 2I from both sides, I'm going to get 4I. And if I add 3j to both sides, I'll get 8j equals 5 multiplied by the acceleration. So divide both sides by 5, and the acceleration vector is given by this result here, which if we want to write it out in separate I and j components, we simply can do like that. But the question actually wanted us to find the magnitude of the acceleration of the particle. So I need to work out mod A, and we simply make use of Pythagoras' theorem in calculating the magnitude of a vector. And this works out to be 4 root 5 over 5 meters per second squared. Now for part 2, to find the particle's displacement after 5 seconds and its direction of motion at this time, we can use virtually any of the SUVAT equations because we have so much information provided. So I'm going to use the fact that r equals ut plus a half at squared. I don't need to adjust this at all because the particle leaves the origin at the start. So at t equals 0, r0 is equal to 0. where that's its starting position. So this particle starts at the origin. We don't need to adjust this SUVAT equation here. So let's substitute in the information. We know that u is equal to 2I minus 3j multiplied by the time, which we know is 5, plus a half multiplied by the acceleration vector, which we know is 4/5 I plus 8/5 j multiplied by the time squared, which is 5 squared. Let's work this out. Remember, you need to collect I components and then j components separately. It's almost like collecting like terms in an algebraic expression, where previously you would have collected x terms and y terms. Now collect I terms and j terms separately. Now you should find you get 20I minus 35j. Now, to find the particle's direction of motion, for the second part here, it's really important, and not everyone always understands this, that to find the direction of motion, we need to use the velocity vector at this time. So we need to find out what v is. So remember, v equals u plus at. Now, I'm going to do this a little bit differently in my layout. I'm going to use column vectors. Remember, the initial velocity is 2I minus 3j. I can write that as 2 minus 3, plus the acceleration vector, which is 4/5, 8/5, multiplied by the time, which is 5. And then we just collect the I components and then the j components separately, but in column format. So this then gives me 6, 5. So the velocity at 5 seconds is 6I plus 5j, or 6, 5, as a column vector. Now, to find the direction of motion, we need to draw the velocity vector. Cannot calculate the direction of motion without having a clear diagram of what the velocity vector looks like. So we know that there are 6 units across and 5 units up in the vector 6, 5. So if we sketch that just quickly, we'll see we get something like that. And then, of course, we want the diagonal here, the resultant. So if that's 6 units along here, that's 5 units along here, then we need to find the direction of motion by finding perhaps an angle. So we could calculate this angle here, theta, which would equal tan to the minus 1, or arctan, of 5/6. And in degrees, that comes to 39.805 ... So we could say that the particle travels at an angle of 39.8 degrees above the horizontal at the time t equals 5 seconds. We could also give a bearing. If you wanted to do that, you'd need to remember to measure this purple angle here, clockwise from the north line. So, second example, a boat is initially at a point with position vector given here. Now that's really important information. That tells us when t equals 0, the position is equal to r0, which is equal to the vector 2i minus 5j, or as a column, which I tend to find preferable, 2 minus 5. Now we know its initial velocity is 1, 2, and we know it's got a constant acceleration, and that's important, which is equal to minus 0.5i plus 1.5j meters per second squared. Now, find the boat's displacement after t seconds. So, we're doing this in general format because we're doing this after t seconds. We don't have a specific value of time. So we can use r, because that's what we're actually looking for, u, which we have, a, which we have, and also t in its general format. So the only variable we're missing here is v. So this means I can use r equals ut plus a half at squared plus r0. Now, why do I have to add on the r0? Because the particle is initially not at the origin. It's at this point here, which we have labelled r0, that we have labelled its position vector as r0. So let's proceed. So u is 1, 2, t is t, plus a half, the acceleration vector, minus 0.5, 1.5, t squared, plus 2 minus 5. Now, there's not a huge amount of simplification that we can actually do here. We could multiply the negative 0.5 and 1.5 by half to simplify them a little bit, but it won't simplify them significantly. Now, part 2, find the boat's distance from the origin after 3 seconds. So you really need to understand what's going on here with this boat. Let's imagine a pair of axes, like this. There's the y-axis or the y-axis, there's the x-axis, and you can see the origin as well. Now the particle starts at this point here, a point which is 2 minus 5. So this vector here is r0, which is 2 minus 5. Can you see? It's 2 units to the right, or in the positive I direction, and 5 units vertically downwards in the negative j direction. So that's the initial starting point. Now, what we know is that the particle is going to travel, and we're interested in where it travels to from this starting point here, which I've just highlighted in red, after 3 seconds. So if t equals 3 seconds, let's substitute into this result here that we have for r and see what we get. So that gives us 3, 6 plus a half multiplied by negative 0.5, 1.5 multiplied by 9 plus 2 minus 5. So remember, collect the I components and the j components separately. And we end up with 2.75 and 7.75. Now, if we had just worked out ut plus a half at squared, we would have found out this pink vector here, i.e. the displacement from the starting point of the motion. But because we adapted our SUVAT equation to include plus r0, we actually have this green vector here, and this green vector is the vector 2.75, 7.75. It tells us the position of the particle relative to the origin after 3 seconds. Now, if we want to know the distance, we then need to work out the magnitude of this vector, so 2.75 squared plus 7.75 squared, and then square root all of this, and we get a result of 8.2234 ... so 8.22 metres to 3 significant figures.